and we're going to talk about electric circuits. And our goal is to understand electric circuits in terms of the microscopic models that we've been dealing with and the terms of the fields, the electric fields that we've been dealing with. And let's just remind you of some things you already know about models of matter. You know that we're going to be dealing with conductors again, okay, because we're going to be talking about charge flow through conductors. And so we know that conductors have a mobile electron C that kind of fills the space, okay, superimposed on top of positively charged ionic cores that each atom gives up an electron to the mobile electron C, okay, and so the electron C kind of fills the space. And then if you are able to have an electric field inside a conductor, then you can cause these charges to flow. And we could run a little demo program that shows this. So the plus charges are the static, immobile ionic cores, and the negative charges that represent the electrons that are free to move. You apply an electric field in this direction, and the force on an electron is then going to be in the opposite direction, so that'll cause it to accelerate. Now, we shows here the charge is kind of moving at a constant rate, which is what eventually happens, or on average happens. We've seen the proportionality between what we call the drift speed and the electric field. Okay, so drift speed of mobile electrons. This is the electric field. And then this is called the electron mobility. How easily the electrons can move through a particular conductor given a particular electric field. It's a property of the material, okay? And in our model, you know, this is kind of the average motion, but in our model we're saying that the electrons will accelerate and pick up speed until they eventually collide with one of these positive ionic cores and lose all their energy and give some of the kinetic energy to the ionic cores, which then start to vibrate around. We interpret that as a temperature increase, as thermal energy. And so if you were plotting the velocity versus time for a mobile electron, you'd see it accelerate to the electric field and then eventually collide and lose all its energy, and accelerate and lose all its energy, and accelerate and then collide and lose all its energy. So on average, you have an average constant speed to these mobile electrons, and so the drift speed is directly proportional to the applied electric field. Okay. Another thing we've seen is that the electron current, little I, is, what's the electron current again? That's what per second? Not coulombs per second, that's the conventional current. This is the just number of electrons per second, right? Little I is the number of electrons per second. And little I can be related to the drift speed, and the formula we would worked out was NA times V. What was little n? Electron density. Okay, little n is the electron density. And that's the number of electrons per volume, right, per cubic meter. Okay, so there's some certain number of electrons, free electrons, mobile electrons, per cubic meter in a particular metal. Again, that's a property of the material, just like the mobility. And then you have A, which is the, what's A? Area. What area? Cross-sectional area. Cross-sectional area of the wire through which the electrons are traveling. Okay. And you can see how the units work out, right? Electrons per meter cubed times meters squared times meters per second gives you electrons per second. Okay, so this is something we've seen before, and we're going to be using it quite a bit in this chapter. And then conventional current, capital I, is just the charge of the electron times that electron current. So this is coulombs per second or amps, right? Okay. All right. So if we have a situation like this, we can create one by just taking a battery or two batteries in series here, and I'm going to connect them to just a little light bulb, and I connect the circuit, and the light bulb lights up. Okay. Pretty exciting. And we have a current, right? We have a current running through the light bulb, and the light bulb, by lighting up, shows exactly this sort of collisions we were talking about, right? Electrons flowing through the filament, colliding with the mobile cores. They give their that kinetic energy goes to heating up these ionic cores, heating up these ionic cores, and that energy is given off as light, right? It gets hot. You can even touch it and feel it get hot. Okay. So here's an example of a simple circuit with a current. Okay. So somehow we're able to create a situation where we have an electric field inside these wires. Okay, these are insulated copper wires that keep driving these mobile electrons. Is this an equilibrium situation? Is this static equilibrium? No. What's true in static equilibrium in a metal? The electrons have stopped moving, right? So clearly the electrons are moving here, right? So this isn't a case where we have equilibrium. So we can therefore have an electric field inside the metal, okay? And this is this is something that's called, we're going to use the term a steady state. Okay, in fact, let's contrast. We have equilibrium versus steady state. So in equilibrium, by definition, the drift speed of the electrons is 0. Okay, in a steady state, it's not equal to 0. Okay, and it's not changing over time. We're not changing with time. Okay, so it's steady. Now, not necessarily, well, as we'll see, the speed might not necessarily be the same everywhere in the circuit, but at a given point, the speed stays constant in time, okay? And therefore, right, little I also is equal to 0, and the electric field, or net electric field inside the wire is equal to 0 when we have an equilibrium situation, but they're not 0 when we have a steady state, and again, they're not varying in time. Okay. And there's one other, we should just introduce this now, there's one other situation which we'll later talk about, which is something called a transient, which is, there's got to be an instant, when I connect the circuit together, it goes from, if I disconnect the circuit, what's that? Steady state or equilibrium? That's equilibrium, right? Because the electric field has got to be equal to 0 because there's no current, there's no mobile charge movement. You can tell that just from the light bulb not lighting up, okay? So we're at a point here where the net electric field inside the wires is 0, no motion, we're at equilibrium. And then I connect the circuit, and all of a sudden we're in a steady state. So there must be some point or some brief amount of time, and it's really brief, at least in this particular situation, where we go from 0 to non-zero. So a transient we'll talk about as a situation where the charges are moving, and that motion is changing with time. Okay, and you can say the same thing about the current and the electric field. Okay, they're not zero, but they are changing with time. That's the key idea behind a transient. We'll talk more about transients as we go along. But I want to focus on a steady state situation for right now and see if we can learn something about it. And let's ask a question here. And in fact, let's back up a little bit. If I have a battery, and this is the positive terminal of the battery, and this is the negative terminal of the battery, what direction are the electrons moving at A? That's not even bothered to poll. What directions are the electrons going to be moving at A? How do they move? They move toward the negative or away from the negative? They would move away from the negative, right? So at this point, we'll talk more about, again, later, how to model a battery. But we can think of this as electrons come out of the negative terminal of the battery. Okay, so they're moving down and to the right at A. So that'd be direction 4. And then at B, they would be moving that way, right? And then they flow back to the positive terminal of the battery. So that's the direction of the drift speed. Okay, so at location A, number 4 would be the direction of the drift speed and the direction of the electron current, right? So let's just draw that again. Negative, positive terminal of the battery. Here's the light bulb. Okay, so electrons, V bar is that way, and little I is that way, and then V bar is that way, little I, same direction. Conventional current, it flows what direction? Other way, right? Capital I would be flowing the other way by definition. Okay. So let's think about the electron current. We know we have an electron current that's electrons are flowing into this light bulb at location A, and then they're flowing out of the light bulb at location B. And we have a steady state. What can we say about the electron current, the rate of electrons per second at A versus at location B? Is the current at A bigger than at B? Is the electron current at A equal to the electron current at B? Or is the electron current at A less than the electron current at B? And we have some disagreement. We have a little over half of us saying that the two currents are equal. Some of us are saying that, well, light bulb's bright, right? So clearly you got to have more current at A than you have at B, right? Because somehow that current's being used up some way to give off the light. Well, let's think about that. We have a certain number of electrons per second flowing into the light bulb. So a certain number of electrons move in every second. And then some smaller number of electrons come out every second. Where are the electrons going? They turn into energy. So electrons annihilate with protons or positrons or something in the filament, and they disintegrate and turn into energy. Is that what's going on? Right? Okay. What do we? Okay. So if electrons are going away, we either have to have a nuclear reaction going on, right? Where electrons are annihilating and just turning into photons. Or if they're just directly going away, if electrons are just actually leaving the system or being sort of directly turned into photons, then what would happen? Yeah, what conservation of what? Okay, so one is conservation of mass, right? We got to have conservation of mass and energy. And the other conservation law we have is charge. Yeah, conservation of charge, right? Because if electrons were just leaving, this thing would be getting more positive and more positive and more positive, right? And I don't think that's happening. You could probably test that if you had a little piece of, if you had a little piece of tape or a little shred of paper and put it near here, and you would see it eventually get repelled and repelled, right? Or if it were positively charged, or attracted if it were neutral or negatively charged. But I'll assert to you that it stays neutral. You can try it out yourself if you like. Okay, so we got a problem. The electrons can't just go away. they can't just accumulate. The only other option is they would accumulate, right? If they come in and stop, then we got another problem because, we have a continuous charge buildup. So the only possible option is that the amount of charge flowing in has got to be equal to the amount of charge flowing out every single second. That really stems from this idea of conservation of charge, plus the idea of we have a steady state. Nothing's changing with time. Okay, so the rate of charge flow stays the same.